This is Laboratory 2. I'm Jim Lauritsen. The purpose of this study is to observe and analyze the video of a falling object that has drag forces in addition to gravitational forces. A computational model based on Newton's second law, the law of gravity, and drag forces proportional to the square of the velocity will be constructed, and predictions of position as a function of time determined. The computational model will be modified to empirically establish a coefficient of drag appropriate for the falling object in the experiment. The experimental setup, the coordinate axes, and a picture of the object used is indicated in this slide. This is the empirical data obtained from the tracker analysis. Two forces will be assumed to be acting on the following object. The gravitational force is indicated by this expression, and the drag force is indicated by the lower expression. These forces will be combined by addition to give a net force that is then applied in Newton's second law. This is the Python code for this study of the computer-generated model. This is the recursive loop in which the gravitational forces and the drag forces are combined and used in Newton's second law. Correction, this is the graphical display of the experimental data as well as the computer prediction. The origin is in the upper left-hand corner. The x-axis is time in seconds. The y-axis is distance in meters, not kilometers as indicated. The orange line is the computer-generated model with no drag factor. The upper blue line is the data obtained from the actual experiment, and the middle yellow line is the computer-predicted model after a drag force has been obtained empirically. This is a comparison of the experimental data and the computer-generated model after the drag force has been empirically established. The first region of low velocity shows close correlation between the two. A middle region shows some deviation between the experimental data and the computer-generated predictions. That is because experimentally the point of mass is difficult to determine in the tracker program. Secondly, there were environmental forces such as wind. And thirdly, the object was moving not only in the y direction, but to some extent in the x-axis. The final portion of the plot shows the region where there is close approximation, and that is because the b drag factor had been adjusted to actually match the experimental data. Terminal velocity is the final constant velocity achieved by a falling object when the magnitude of the gravitational force is equal to the magnitude of the opposing drag force. That is given by the following expression. In this study, the calculated terminal velocity is indicated as 2.6943 meters per second, and the observed experimental terminal velocity was 2.705 meters per second, a reasonable correspondence. The question of negative initial velocity was raised. By throwing an object downward, initial velocity becomes negative. The terminal velocity would not change as this initial velocity does not enter into the expression given below. This is confirmed by using the Python model at different initial velocities. The purpose of this study is to observe and analyze the video of a following object that has drag forces in addition to gravitational forces. A computational model based on Newton's second law, the law of gravity, and a drag force, indicated by the following expression, was constructed and studied. It was found that a value of b, the coefficient of drag, could easily be determined to correspond to the experimental data. A terminal velocity was quickly achieved in the experimental study and in the calculated model. Finally, it was shown that because of the nature of the drag force, any downward initial velocity has no effect on the terminal velocity.